Something from nothing? Imagine opening your eyes to the entire universe, stars, galaxies, black holes, time itself, and realizing it may have all come from nothing. Not empty space, not a quiet void, but true, absolute nothingness. No atoms, no light, no laws of physics. Nothing. And yet, here we are. How is that even possible? How could something as vast, complex, and structured as the universe emerge from literally nothing at all? This question lies at the edge of science and philosophy. It has fascinated thinkers for thousands of years, and now, for the first time in human history, we may be getting close to an answer. Not a mystical one, but one grounded in the laws of quantum physics, cosmology, and the geometry of spacetime itself. This is the story of the universe's ultimate magic trick, existence from nothing. Defining nothing. Before we explore how the universe could emerge from nothing, we must ask a seemingly simple question. What is nothing? In everyday life, we treat nothing as the absence of stuff. An empty room, a blank page, or a vacuum, these all feel like nothing. But to physicists, even a perfect vacuum isn't truly empty. It's filled with quantum fields, zero-point energy, and virtual particles constantly flickering in and out of existence. True nothingness, if it even exists, would mean no space, no time, no energy, no laws, no quantum fields. But here's the twist. The laws of physics, particularly quantum mechanics, may actually require something to emerge even from nothing. In fact, they might make it inevitable. Quantum fluctuations and virtual particles. At the heart of quantum physics lies a strange and beautiful concept. The vacuum isn't empty. Even in its lowest energy state, space is teeming with uncertainty. Particles and antiparticles spontaneously appear, interact, and vanish in incredibly short timescales. These are known as virtual particles. This phenomenon is not science fiction. It has real, measurable effects. The Casimir effect. Two uncharged metal plates, placed close together in a vacuum, attract each other due to pressure from virtual particles. Hawking radiation. Black holes slowly evaporate because virtual particles at the event horizon become real. One falls in, one escapes. So if particles can emerge temporarily from quantum nothing, could an entire universe emerge from a deeper kind of quantum fluctuation? Many physicists think so. And that brings us to the realm of cosmology and the birth of everything we know. Inflation from nothing. The early universe underwent a rapid exponential expansion called inflation. Within a fraction of a second, space itself grew from subatomic size to cosmic proportions. But where did this inflation come from? Some models suggest that a quantum fluctuation in a primordial field, like the hypothetical inflaton field, could trigger inflation. If the energy conditions were just right, that fluctuation could have led to the explosive expansion of a pocket of space, our universe. Importantly, this process does not require pre-existing space or time. Inflation could, in principle, begin from a quantum fluctuation within a state that is, by all practical purposes, nothing. In this view, the universe is a quantum event, and like all quantum events, it doesn't require a classical cause. Quantum gravity and the birth of spacetime. General relativity breaks down at the singularity, the theoretical point of infinite density at the start of the Big Bang. To go further back, we need a theory of quantum gravity, a fusion of general relativity and quantum mechanics. One such attempt is loop quantum gravity (LQG). In this theory, space and time are not continuous, but made of tiny discrete units, or loops. These loops fluctuate and can transition from a non-spatial, non-temporal state into full-blown spacetime. Another approach is string theory, where the fundamental units of reality are vibrating strings of energy, possibly existing in higher dimensions. In certain models, universes can tunnel into existence from a quantum vacuum. These ideas all point to one thing. Spacetime itself, the fabric of the universe, may not be fundamental. It may emerge from something deeper, or from nothing at all. Vacuum states and the multiverse. Modern physics suggests that what we call nothing might actually be a false vacuum, a temporary metastable state with higher energy than the true vacuum. Quantum tunneling from a false vacuum to a true vacuum could trigger the birth of a universe like a bubble forming in boiling water. This is a key part of eternal inflation theory, which leads to a multiverse, an endless number of bubble universes, each with different physical laws. In this scenario, universes are not special. They pop in and out of existence like quantum bubbles. Our universe may be just one of many, and its emergence from nothing may be the rule, not the exception. Nothingness in different theories. Let's revisit the idea of nothing under several different theories. Classical nothing, the absence of matter in empty space. Quantum nothing, the absence of particles, but still fields and laws. Metaphysical nothing, the absence of everything, no space, time, laws, or logic. Most scientific models operate with quantum nothing, the absence of particles, but not of structure. The true metaphysical nothing may be philosophically meaningful, but science requires a framework, and that framework still contains potential. Philosophical reflections. Philosophers have asked for centuries, why is there something rather than nothing? Some argue that nothingness is less stable than something, and so, perhaps existence is inevitable. Others suggest that existence doesn't need a cause, it simply is. Still others invoke logic itself, suggesting that if existence is possible, it must occur. Religious or metaphysical explanations invoke a creator or purpose, but the scientific view tries to describe how the universe could arise from nothing without needing external purpose. The mystery remains profound, but science gives us tools to explore it meaningfully. Evidence and limits. Is there evidence the universe came from nothing? Not directly, but observations of the CMB, the distribution of galaxies, and the success of inflationary models support the idea of a quantum origin. We also observe that the total energy of the universe may be zero positive matter energy and negative gravitational energy canceling out. Some theories even propose that the laws of physics are self-generating, arising naturally from mathematical logic or symmetry principles. Could it happen again? If a universe can emerge from nothing once, could it happen again? In some multiverse models, it happens endlessly. Quantum fluctuations in a timeless background can spark countless universes. We may even be living in one bubble among infinite others. The concept of cyclical cosmology also suggests that the universe undergoes infinite cycles of birth, death, and rebirth, though not necessarily from nothing, but from a previous phase. Whether the process is repeatable or not, it suggests that existence is far more dynamic than we once imagined. The meaning of nothing. So what does it mean to say the universe came from nothing? It means that the universe with all its galaxies, time, energy, and consciousness may have no origin point in the way we traditionally think. No need for a creator, no edge of space, no before. It means that physics, math, and quantum mechanics may be all we need to explain the greatest mystery of all, why there is something rather than nothing. And perhaps most importantly, it means we as conscious beings capable of asking these questions are part of the mystery. Our ability to think, reflect, and seek truth is not separate from the cosmos. It is the cosmos awakening to itself. If you enjoyed this exploration, don't forget to like, subscribe, and share this journey with other cosmic thinkers. The universe may have come from nothing, but our curiosity makes it truly alive. The signal that changed everything. In the vast silence of space, one signal broke through. It wasn't a random burst of static. It had structure, a pattern. Purposed IT lasted just 72 seconds, but it made history. The year was 1977. A powerful radio telescope in Ohio picked up a narrowband radio signal from the constellation Sagittarius. It was so precise, so unusual, that the astronomer who discovered it circled the printout and wrote a single word in the margin. Wow! For decades, scientists have searched the skies for a repeat. They've built massive telescopes, scanned billions of stars, and listened to the cosmic whisper of the universe, all to answer one ancient question. Are we alone? In this video, we'll explore the science behind the search for extraterrestrial intelligence SETI, the strange signals we've detected, and what it would mean to truly receive an intergalactic message. Because if someone out there is trying to talk to us, we need to know how to listen. The science of SETI listening to the stars. The search for extraterrestrial intelligence, or SETI, is a scientific effort to detect signals from intelligent alien civilizations. Unlike science fiction, SETI is based on real astronomy, radio physics, and data analysis. SETI researchers focus on narrowband radio signals' concentrated frequencies that are unlikely to be produced by natural astrophysical processes. Such signals stand out like a lighthouse beam in a sea of noise. SETI researchers focus on narrowband radio signals' concentrated frequencies that are unlikely to be produced by natural astrophysical processes. Such signals stand out like a lighthouse beam in a sea of noise. Instruments like the Allen Telescope Array, Breakthrough Listen Project, and China's Fast Telescope scan the skies, analyzing billions of data points in search of anything that breaks the cosmic pattern. But it's not just radio. SETI now includes optical signals, laser flashes, and even technosignatures, potential signs of alien technology, like Dyson spheres or artificial atmospheric chemicals. The science is real, the search is serious, and the implications are profound. The signals we've heard and what they might mean. Over the decades, scientists have received dozens of signals that sparked intrigue and sometimes panic, The WOW! Signal 1977, a one-time 72-second burst from Sagittarius. Never repeated. Still unexplained. FRB's fast radio bursts powerful. Millisecond radio bursts from distant galaxies. Some repeat, some don't. Their origin remains a mystery. Chigo 2+14 at 2004. A signal detected multiple times near the waterhole frequency, where SETI expects alien signals. But it drifted in frequency, suggesting a technical glitch, or something moving fast. None of these signals have been confirmed as extraterrestrial, but they remind us the universe is loud, and we're only beginning to understand what we're hearing. What counts as a message? Not every signal is a message a real message would likely have. Deliberate structure, mathematical patterns, repetitions, narrow bandwidth not caused by natural phenomena, repeatability we can detect it again, non-random source fixed direction in the sky. Many scientists believe that if we receive a message, it will begin with something universal like prime numbers, the Fibonacci sequence, or the periodic table. Something that says, "We know math. Do you?" Others speculate about messages hidden in light pulses or neutrino beams using physics itself as the language. How we're watching telescopes, algorithms, and AI. Modern SETI is not just people wearing headphones. It's massive arrays of radio dishes, machine learning, and petabytes of data. Breakthrough Listen analyzes petabytes of radio data using AI to spot anomalies. The Allen Telescope array scans the sky in multiple directions. Optical SETI looks for laser pulses that could carry encoded information. AI is increasingly critical. With billions of possible signals, only machines can spot patterns too subtle or complex for humans. How would we respond? Imagine we receive a real message. It's verified, repeated, structured. Undeniably artificial. What next? There is a protocol, the SETI Post-Detection Protocol, which outlines how scientists should confirm, share, and respond to such a discovery. It includes global scientific verification, notification of international bodies, no immediate response, only after global consensus. Why? Because replying might reveal our location, our technology, our vulnerability. Some advocate for silence. Others say we must answer, if only to show we are here. What if no one answers back? What if we search for centuries and hear nothing? This silence is called the Fermi paradox. If the universe is full of planets and time, where is everyone? Possible answers. Where too early intelligent life takes time. Civilizations self-destruct before they can communicate. Advanced beings observe us silently. Or we really are alone. Silence is not nothing. It tells us something about the rarity or fragility of life. Philosophical reflections. What if we are not alone? If we detect a true intergalactic message, it would change everything. Our understanding of consciousness, religion, philosophy, science all would shift. But even without contact, the search itself is profound. IT shows we are curious, hopeful, united by wonder, because to listen to the stars is to believe they might listen back. The sky is not silent. We may not have received a reply yet, but the search continues. Every beam we scan, every signal we decode, is a whisper in the cosmic dark, and maybe, just maybe, someone out there is listening too. If this made you think, inspired you, or gave you chills, like, share, and subscribe for more explorations into the great unknown.
Close your eyes and imagine you're looking up into the night sky, and you see a faint reddish star shining back. You may not know it, but that star is the home of the nearest exoplanet to our own, and it's a world that could potentially provide a haven for life as we know it. We're talking about Proxima Centauri b, the closest exoplanet to our Earth, close to Earth's twin according to the data. How would life adapt to such a world? Located 4.2 light years from Earth, the Alpha Centauri system, a triple star system, is home to Proxima Centauri, a tiny red dwarf star. It orbits around a pair of sun-like stars, Alpha Centauri A and B. And right there, embedded in the habitable zone of its star, is Proxima Centauri b, the gem of this star system. Proxima b orbits its star at a distance of just 4.6 million miles. That's incredibly close, just 5% of the distance between Earth and the Sun, and even closer than the distance between Mercury and the Sun. However, since Proxima Centauri is only 1/10 the size of our Sun, the star's habitable zone is much closer to it. But the Cinderella zone, being so close to the star's surface, also has its drawbacks. Because of the planet's close proximity to its star, it becomes clingy. One side of the planet always faces the star, becoming a fallen desert, while the other side remains perpetually in darkness, exposed to the cold vacuum of space. This can make habitability difficult, and such temperature extremes on Proxima Centauri b make it difficult for life to exist. But hold on, the plot thickens in the twilight zone, where the light and dark sides intertwine. Here, temperatures reach a sweet spot, potentially making it a haven for life. Between the scorched earth and the icy abyss, this Goldilocks zone could be the cosmic sweet spot where life might adapt and thrive. Astronomers first stumbled upon Proxima b in 2016 using the radial velocity method. Imagine detecting a minuscule star swaying in a cosmic waltz, a dance induced by the gravitational tug of a neighboring planet. A closer look revealed the hidden partner, Proxima Centauri b. Upon meticulous scrutiny, scientists found that Proxima b bears a striking resemblance to Earth, scoring an impressive 0.87 ESI, a metric gauging its Earth-likeness based on factors like size, mass, temperature, and density. Proxima Centauri b emerges as a promising candidate for extraterrestrial life. Yet, despite the high ESI score, mysteries shroud Proxima b. Does it boast a life-sustaining atmosphere? That's the cosmic conundrum. The star it orbits, Proxima Centauri, is a fervently active red dwarf, unleashing stellar tantrums in the form of intense stellar wind pressures, over 2,000 times more potent than Earth's solar wind. This tempest raises the unsettling prospect of the planet's atmosphere being stripped away over time, rendering it barren and inhospitable. Life on Proxima b, in the face of solar flares and relentless winds, might have devised ingenious survival strategies. Could the depths of its oceans harbor life shielded from the cosmic onslaught? On Earth, we've witnessed life adapting to intense radiation, like coral polyps evolving fluorescent proteins to counteract harmful ultraviolet rays. Proxima b's conditions might mirror this resilience, offering a tantalizing glimpse into the adaptability of life in the cosmos. As we delve into the potential habitability of Proxima Centauri b, it raises profound questions about the nature of life beyond our pale blue dot. Could life on Proxima b share uncanny similarities with earthly life forms? Evolutionary convergence, a universal principle that suggests that disparate species may evolve analogous adaptations in response to comparable environmental challenges. If Proxima b supports life, it might just be life as we least expect it. A mirror reflection of the life forms we know so well. Join us as we embark on this cosmic exploration, unveiling the mysteries of Proxima Centauri b, the enigmatic neighbor in our cosmic backyard. And as you ponder the potential parallels between Earth and Proxima b, we invite you to share your thoughts in the comments below. What aspects of Proxima b's potential habitability intrigue you the most? What earthly life forms do you think might find cosmic counterparts on this distant exoplanet? Let the cosmic conversation begin. As we delve into the study of the potential habitability of Proxima Centauri b, profound questions arise about the nature of life beyond our pale blue dot. Could life on Proxima b bear a remarkable resemblance to terrestrial life forms? The principle of evolutionary convergence, a universal principle, suggests that different species can develop similar adaptations in response to similar environmental challenges. If there is life on Proxima b, it may be the kind of life we least expect, a reflection of the life forms we are familiar with. Join us as we embark on this cosmic journey, uncovering the secrets of Proxima Centauri b, a mysterious neighbor in our cosmic backyard. And while you ponder the possible parallels between Earth and Proxima b, we invite you to share your thoughts in the comments below. What aspects of Proxima b's potential habitability intrigue you the most? What Earth-like life forms do you think could find cosmic doppelgangers on this distant exoplanet? Let's start a cosmic conversation.
What if everything is an illusion? Close your eyes. Imagine standing in front of a vast wall perfectly black, smooth and infinite. You reach out your hand, but instead of touching substance, it dissolves into light. Nothing is solid. Nothing is fixed. What if everything, your body, your memories, even space and time, isn't as real as it seems? What if the universe itself is a projection? This isn't science fiction. It's one of the boldest, most mind-bending ideas in theoretical physics today, the holographic principle. The suggestion that our entire 3D universe might be a shadow, a projection of information encoded on a distant 2D surface. In this documentary, we'll journey into black holes, quantum information, string theory, and the boundaries of space and time to uncover whether reality is truly holographic. The origin of a radical idea. In the 1970s, a Dutch physicist named Gerard T. Hooft was studying black holes and quantum gravity when he made an astonishing proposal. What if all the information contained in a region of space could be described by information on its boundary? Later, the idea was expanded by Leonard Susskind, who connected it to string theory. Susskind argued that just as a hologram stores a 3D image in a 2D format, so too could the universe store all its physical information on a 2D surface, and yet create the illusion of 3D reality. They weren't alone. The proposal was deeply rooted in attempts to solve one of the greatest paradoxes in physics, the black hole information paradox. Black holes, according to general relativity, seem to destroy everything that falls into them, including information. But in quantum mechanics, information can't be destroyed. Something had to give. The solution? Information may never really be lost inside a black hole, because it could be encoded on its surface. That's where the holographic principle was born. black holes and the edge of reality. Black holes are not just cosmic monsters. They are laboratories of reality. In 1974, Stephen Hawking shocked the world by showing that black holes are not completely black. They emit radiation now known as Hawking radiation due to quantum effects near the event horizon. Over time, this radiation can cause the black hole to vaporize. But if the black hole disappears, what happens to the information about the matter that went into it? If it disappears completely, it violates quantum theory. If it persists, where is it stored? Hawking, Susskind, and others argued vehemently. A solution began to emerge. Information about what falls into a black hole is stored not in its interior, but on the event horizon, the two-dimensional surface. This led to an incredible realization. Perhaps the entire universe works the same way. Just as a black hole encodes its contents on its surface, the cosmos may be the same. The mathematics of holography. In 1997, physicist Juan Maldacena made a stunning breakthrough. He proposed a duality between two radically different theories. Gravity theory in 5D spacetime including our usual dimensions, quantum field theory without gravity at the 4D boundary of this space. This became known as the ADS or CF correspondence, an exact mathematical realization of the holographic principle, although the particular geometry anti-de Sitter space does not describe our universe. The universe as information. At the heart of the holographic principle is one strange idea. Information is more fundamental than matter. Everything we see around us may be the result of bits, tiny units of quantum information interacting, processing, and evolving. This isn't just theory. Scientists like Seth Lloyd and John Archibald Wheeler have proposed that the universe is fundamentally a quantum computer processing information at the smallest scales. Wheeler's famous phrase "it from bit" suggests that every particle, every field, and every interaction arises from binary yes-no choices from logic, not substance. Your body, your thoughts, the sun, the galaxies all might be emergent phenomena built from pure information, unfolding on a lower dimensional surface. Could we ever prove it? If the holographic principle is true, can we test it? Physicists are trying. Some look at cosmic microwave background data, searching for statistical fingerprints of a holographic geometry. Others examine quantum entanglement and the structure of spacetime itself. Others examine quantum entanglement and the structure of spacetime itself. Experiments like the Fermilab holometer aim to detect holographic noise, tiny jitters in spacetime that might reveal its digital nature. Far. No conclusive evidence, but hints keep coming. Theories involving emergent gravity, tensor networks, and quantum error correction are painting a picture of spacetime as an illusion, built from deeper rules. If true, it would mean that you are not truly in space, but rather, your entire reality is a projection from a distant, invisible boundary. Consciousness and the hologram. Some thinkers go even further. Could consciousness itself be a holographic phenomenon? Neuroscientist Carl Pribram and physicist David Bohm suggested that the brain doesn't store information like a computer, but like a hologram, distributed, overlapping, resilient. Perhaps reality and mind are both projections, not separate, but reflections of deeper structures. Quantum consciousness remains speculative, but one thing is clear: The holographic principle forces us to rethink what we mean by real. Maybe the boundary between mind and universe is itself an illusion. What does it all mean? If the holographic universe is real, space is not what we think it is. Time may be an emergent illusion. Our world is deeply connected to an invisible boundary we cannot see. This isn't just theory. It's a call to rethink physics, philosophy, and perception itself. We may live inside a cosmic illusion, but that illusion is governed by rules we're beginning to decode. We are shadows of code. Awakening. The wall and the light. Remember that wall of blackness at the beginning? Maybe it's real. Maybe we're seeing its projection. Maybe we've spent millennia staring at the shadows on the wall, unaware that reality lies not within the cave, but on the wall itself. The holographic principle doesn't diminish the universe. It reveals how much more there is to understand, and perhaps how deeply we are already a part of it. If you found this journey fascinating, subscribe for more mind-expanding cosmic explorations. Ten space myths that everyone still believes, and why they're wrong. You think you understand the universe? You don't. You've seen the stars, the moon, the galaxies. But what if I told you that almost everything you've ever heard about them is completely, gloriously wrong? So today, we're going to destroy 10 space myths that survive school books, memes, and your uncle who swears he saw UFOs on vacation. And if you already know all of them, congratulations, you get the NASA-approved Genius of the Internet badge. Let's start with the easy ones, and then go straight into the ones that will melt your brain. Myth number 1. The moon has a dark side. No, it doesn't. There's no side of the moon that lives in eternal shadow, full of space vampires. The moon is tidally locked, which means it always shows the same face to Earth. But it still rotates, and every part of it gets sunlight over the course of a lunar month. That's 27.3 days, not 30, and definitely not depending on your mood. So yes, there's a far side, but it gets sun. It's not dark. It's just shy. And if anyone says otherwise, ask them how werewolves keep up with the lunar cycle. Myth number 2. Astronauts float because there's no gravity in space. If you think the astronauts are in zero gravity, then surprise, gravity is still 90% as strong up there as it is where you're sitting. They float because they're falling constantly. The entire space station is in permanent freefall around Earth. It's like jumping off a building that keeps curving away underneath you. So the next time you see astronauts floating, remember, they're falling forever. Romantic, right? Myth number 3. You can see the Great Wall of China from space. No, you can't. It's 7 meters wide. You're 400 kilometers up. That's like spotting a human hair from across a football field. Even astronauts say the same thing. You can't see the wall, but you can see cities, deserts, roads, and airports. And honestly, the Great Wall would be easier to spot if it had LED lighting and a Starbucks. Myth number 4. Space is completely empty. Nope, space is not empty. It's just very bad at being full. Even the emptiest space contains about 1 atom per cubic meter, which sounds tiny, until you realize how much nothing there actually is out there. There's plasma, dust, cosmic rays, dark matter. The whole universe is a low-density soup. So yes, space looks empty, but technically, it's the biggest landfill ever made. Myth number 5. The Big Bang was an explosion. No, it wasn't. There was no boom, no fireball in the middle of nowhere. It was expansion, not explosion. Space itself began stretching, faster than light, everywhere at once. There was no center, because every point in the universe was the center. Think of it as the dough of a cosmic pizza expanding. And you, yes, you, are one of the pepperoni slices getting further from the others. And the universe is still rising in the oven. If the Big Bang happened everywhere at once, then technically, it's still happening inside you right now. Myth number 6. The sun is yellow. Our teachers lied to us. The sun is not yellow. It's pure white. It only looks yellow because Earth's atmosphere scatters the blue light, just like it makes the sky blue and sunsets orange. If you looked at the sun from space, which you shouldn't, it would shine bright white like a cosmic LED. Oh, and calling it a yellow dwarf? Yeah, that's just a branding issue. The sun is neither yellow nor a dwarf. Marketing Department of the Milky Way, 0/10. Myth number 7. The universe has an edge. People imagine the universe like a giant balloon floating in space, but there's no outside. Space itself is what's expanding. If you traveled in a straight line long enough, you wouldn't hit a wall. You'd just end up where you started, like walking around a sphere. So no, there's no edge to fall off. No cosmic border patrol. Just endless curvature. If the universe doesn't have an edge, then where exactly do we draw the line between something and nothing? Myth number 8. Stars twinkle because they flicker. Stars don't flicker. The atmosphere does. Their light passes through kilometers of moving air, and that turbulence bends light slightly, making stars twinkle. If you went to the moon, stars wouldn't twinkle at all. They'd shine steady and sharp, like tiny needles of light piercing the dark. So next time you wish upon a twinkling star, you're really wishing on atmospheric distortion. Romantic, isn't it? Myth number 9. Seasons are caused by distance from the sun. Nope. If that were true, it'd be summer everywhere at once. Seasons happen because Earth is tilted minus 23.5. That tilt means sunlight hits each hemisphere differently throughout the year. When you're tilted toward the sun, you get longer, hotter days. Summer. Tilted away, winter. So if you live in Europe and it's sunny in July, people in Australia are freezing in the dark, questioning their life choices. Myth number 10. Nothing can escape a black hole. Technically, not true. Stephen Hawking said even black holes leak, slowly. Tiny pairs of quantum particles appear at the event horizon. One falls in, the other escapes, stealing a tiny bit of the black hole's energy. That's Hawking radiation. It's so slow, it would take longer than the age of the universe for a black hole to evaporate. But it means even darkness fades eventually. If even black holes can die, then maybe nothing in the universe, not even death, lasts forever. The universe is a terrible liar. So, how many myths did you believe? Be honest and write it in the comments. The universe doesn't care if we understand it, but we do. That's what makes us human. Because every time we uncover a myth, we're not just learning about space, we're learning about ourselves. And if you already knew them all, well, you get your virtual Skynet medal. See you in the next one. And don't forget to question everything.
Welcome to our cosmic journey, where we will delve into the most mysterious and captivating corners of the universe. In this video, we will embark on a journey beyond the starry sky, uncovering the secrets of black holes, neutron stars, and pulsars, exploring the mysteries of dark matter and dark energy, the vast world of exoplanets, and the majestic power of quasars. Our journey begins with the enigmatic black holes, entities so powerful that even light cannot escape their gravitational grasp. We will continue unraveling the mysteries of this universe, investigating neutron stars and pulsars, their extraordinary properties, and their influence on the surrounding cosmic space. Then awaits our immersion into the mysterious world of dark matter and dark energy, which form the foundation of the cosmic fabric and remain among the greatest puzzles for scientists worldwide. The search for extraterrestrial life on exoplanets prompts us to contemplate the probability of the existence of other worlds similar to Earth, and what forms of life may exist there. Finally, we will take a glimpse at quasars and active galactic cores, serving as the key to understanding the early universe and its evolution. Join us on this fascinating journey to explore the greatest mysteries of the cosmos and learn more about our place in this vast universe. The journey into the darkest corners of the universe begins with one of the most mysterious and powerful phenomena: black holes. These cosmic giants not only consume everything that comes too close to them, including light, but also play a crucial role in the formation of galaxies and the cosmic structure as a whole. Black holes come in different types, from stellar, with masses several times greater than that of the Sun, to supermassive ones located at the centers of galaxies, having masses millions or even billions of times greater than the solar mass. But how do they form? When a massive star exhausts its fuel, it can explode as a supernova and collapse into a black hole if its mass is large enough. One of the most astonishing aspects of black holes is the event horizon, the boundary beyond which nothing can return. Near this boundary, time slows down to the extreme, creating a phenomenon that remains the subject of intense scientific research. Studying black holes not only reveals the mysteries of gravity and space-time, but also provides clues about how the universe might have originated and where it is heading. Modern astrophysicists explore black holes using the most powerful telescopes and space observatories, attempting to understand their structure and influence on the surrounding space. The most exciting discoveries in recent years include observations of gravitational waves produced by the collisions of black holes, and the first ever direct image of a black hole's event horizon, captured by the Event Horizon Telescope project. These studies not only confirm the existence of black holes, as predicted by Einstein's general theory of relativity, but it also opened new frontiers in our understanding of the very fabric of the universe. After exploring black holes, our cosmic journey leads us to other equally fascinating objects in the universe: neutron stars and pulsars. These cosmic phenomena are remnants of stars that have undergone supernova explosions but did not become black holes. Instead, their cores compress to a state where the space between atoms disappears, leaving a dense core composed almost exclusively of neutrons. Neutron stars are incredibly dense objects. Imagine the mass exceeding that of the Sun is compressed into a sphere with a diameter of only about 20 kilometers. Their gravity is so strong that if you could take a spoonful of neutron star matter, it would weigh about 1 billion tons. Another amazing phenomenon associated with neutron stars is pulsars, rapidly rotating neutron stars that emit powerful beams of radio waves and other forms of electromagnetic radiation. If the beam of these waves is directed towards Earth, astronomers can observe regular pulses, serving as cosmic beacons with precision comparable to atomic clocks. Pulsars play a key role in astrophysics, helping scientists test theories of gravity, study interstellar space, and even navigate spacecraft. One of the most well-known pulsars is PSR B19Y+21, discovered in 1967, marking one of the greatest achievements in the history of astronomy. Neutron stars and pulsars, these extraordinary cosmic objects, remind us of the fantastic processes occurring in the universe and the significant role that stars continue to play even after their death, influencing the development of the cosmic environment. Continuing our journey through the mysteries of the universe, we come to one of its most intriguing aspects: dark matter and dark energy. These two components make up a large part of the universe's content, yet they remain practically elusive to our senses and instruments. Dark matter is a form of matter that does not emit or reflect light, making it impossible to see directly with telescopes. Nevertheless, scientists can observe the influence of dark matter on visible objects and structures in space, such as galaxies and galaxy clusters. It affects their rotation and motion within them, providing us with indirect evidence of its existence. Dark energy is even more mysterious. It is an unknown form of energy that permeates the entire universe and exerts a repulsive force, accelerating its expansion. Contrary to gravitational attraction, which should slow down the universe's expansion, dark energy acts in the opposite direction, and its nature remains one of the greatest mysteries of cosmology. Modern science asserts that dark matter and dark energy together make up about 95% of the universe's content, leaving only 5% for everything else we can observe, from the smallest particles to galaxies. This discovery not only underscores how little we know about the universe, but also raises new questions about its origin, structure, and fate. Dark matter and dark energy remain at the forefront of attention for astrophysicists and cosmologists worldwide. Unraveling their mysteries could fundamentally change our understanding of the universe and humanity's place in this vast and incomprehensible world. Moving forward in our cosmic journey to one of the most exciting frontiers of modern astronomy, the study of exoplanets and the search for extraterrestrial life. Exoplanets are planets orbiting stars beyond our solar system. Their existence implies the remarkable possibility of life beyond Earth. Since the first confirmed discovery of an exoplanet in the early 1990s, astronomers have found thousands of such worlds, each unique in its own way. Some of these planets resemble Earth, with a solid surface and possibly even liquid water, a key element for supporting life as we know it. One of the significant achievements in this field is telescopes capable not only of detecting exoplanets, but also analyzing their atmospheres for the presence of chemical elements that may indicate the presence of life. For example, the detection of water, oxygen, or methane molecules could be a sign of biological activity. The search for extraterrestrial life is not limited to finding Earth analogs. Scientists are also interested in less hospitable worlds, including gas giants and icy planets, exploring the diversity of conditions under which life could exist. At present, there is no direct evidence of extraterrestrial life, but each new discovery brings us closer to answers to eternal questions. Are we alone in the universe? What are the conditions for the emergence of life on other planets? The exploration of exoplanets opens exciting perspectives and prompts us to reconsider our place in the cosmos. Continuing our cosmic journey, this time delving into the depths of the brightest and most powerful objects in the universe, quasars and active galactic nuclei, AGN. These astronomical phenomena bear witness to the most extreme and energetically saturated processes in space. Quasars are extremely bright and distant objects, emitting radiation that can exceed the luminosity of entire galaxies composed of hundreds of billions of stars. They represent active galactic nuclei, fueled by supermassive black holes at their centers. As matter falls into the gravitational trap of the black hole, it heats up to incredible temperatures, emitting an enormous amount of energy in the process. Active galactic nuclei, or AGN, constitute a broad class of objects that includes not only quasars, but also other types such as radio galaxies and blazars. All of them demonstrate high activity in the central part of galaxies and are crucial for understanding the evolution of galaxies and the universe as a whole. Research on quasars and AGN not only helps astronomers better understand the nature of black holes and the processes occurring when they consume matter, but also provides a unique opportunity to study the state of the universe in its early stages. After all, the light from the most distant quasars that reaches us embarked on its journey billions of years ago. Unraveling the mysteries of quasars and active galactic nuclei, scientists come closer to understanding the most fundamental questions about the structure and evolution of the universe, as well as the nature of matter and energy itself. As we conclude this fascinating journey through the most amazing and mysterious corners of the universe, it becomes evident how vast and diverse our cosmos is. From enigmatic black holes to twinkling neutron stars, from mysterious dark matter to captivating studies of exoplanets. Each topic opens up incredible perspectives for exploration and understanding. These discoveries not only expand the boundaries of our knowledge about the universe, but also remind us of how little we know and how much there is yet to discover. After all, each answer begets new questions, and every discovery leads to new mysteries. The universe is full of wonders, and each new study brings us closer to understanding our place in this boundless and magnificent cosmos. However, so much remains beyond our understanding, awaiting its moment to be unveiled. What do you think will be the next major breakthrough in astronomy? Black holes, dark matter, exoplanets, or something completely unexpected? If you had the opportunity to embark on a cosmic journey to any of the objects mentioned in the video, where would you choose to go and why? Black holes, neutron stars, distant exoplanets? What arouses your greatest curiosity? Mercury is the most compact planet in our solar system, only slightly larger than Earth's moon. This planet, only 58 million kilometers from the Sun, is its nearest neighbor, which makes it extremely interesting to study. A Mercurian day lasts 59 Earth days, while a Mercurian year lasts only 88 Earth days. But with a solid surface covered with craters like the Moon, Mercury belongs to the terrestrial group of planets. Its exosphere, an extremely rarefied atmosphere, is rich in oxygen, sodium, hydrogen, helium, and potassium, but it is too thin to pressurize or trap heat. In addition, Mercury lacks both satellites and rings. Spacecraft visits to Mercury have been rare. Mariner 10 in the mid-1970s and Messenger, which in 2011 became the first spacecraft to enter Mercury's orbit after 3 flybys near the planet. Life on Mercury is hardly possible due to the extreme temperature conditions ranging from 430 degrees Celsius during the day to 418 degrees at night. Observing the Sun from Mercury's surface would provide a spectacle 3 times its apparent size from Earth. The ancient Sumerians were familiar with Mercury as early as 5,000 years ago, associating it with the god Nabu. The Romans named the planet after Mercury, the god of trade and travel, for its rapid movement across the skies. Interestingly, Greek astronomers pioneered the idea that Mercury and Venus revolve around the Sun, not the Earth. What makes Mercury special is its ability to reach daytime temperatures of up to 450 degrees due to its proximity to the Sun, while the night side of the planet cools to 100 degrees. This is due to the lack of an atmosphere capable of trapping heat, making a temperature gap of more than 600 degrees, the largest in the solar system. The presence of numerous craters on Mercury, due to the lack of atmosphere and proximity to the Sun, makes its surface similar to the lunar surface, emphasizing the uniqueness of this small but interesting planet. Studies have shown that Mercury has a peculiar magnetic field, which is surprising for such a small planet. This field is hundreds of times weaker than Earth's, but its existence confirms its complex internal structure. In 2019, the Bepi-Colombo mission, a joint project of the European Space Agency and the Japan Aerospace Exploration Agency, was sent to Mercury to study its surface, magnetic field, and internal structure. It is expected to reach Mercury in 2025, promising new discoveries about the solar system's smallest planet. Despite extreme temperatures, a water ice has been found in craters near the poles of Mercury, which sunlight never reaches. This discovery, made by the Messenger spacecraft, indicates that water may exist even in the most unexpected places. Because of the unique relationship between the periods of Mercury's rotation around its axis and its orbit around the Sun, a day on Mercury lasts twice as long as a year. This means that in the time it takes Mercury to make one complete revolution around the Sun, only half a day passes on the planet. Mercury is gradually shrinking. By studying craters and faults on the surface, scientists have concluded that the planet has shrunk by about 7 kilometers in diameter over the past billion years. This contraction is due to the cooling and shrinking size of the planet's iron core. Mercury's orbit has the greatest eccentricity of any planet in the solar system. This means that the distance between Mercury and the Sun varies greatly. At perihelion, closest point to the Sun, it is about 46 million kilometers, and at aphelion, farthest point, it is about 70 million kilometers. Mercury's magnetic field, although weaker than Earth's by a factor of about 100, is still significant for such a small planet. It indicates an active iron core, which probably still generates magnetism through convective motion. Because of the lack of atmosphere, meteors do not burn up as they enter Mercury's atmosphere, as they do on Earth. Instead, they collide with the surface, creating new craters. This constant bombardment contributes to the planet's unique landscape and constant renewal of its surface. These additional facts emphasize the complexity and uniqueness of Mercury, making it one of the most interesting objects to study in our solar system.